Lovely to see you all here, and welcome to anyone who's online as well. This is my talk on reliability engineering, and I'm going to go straight into it. If you want to know who I am, there's a slide at the end. There's about 20 slides in the presentation if you're a kind of person who wants to keep track of how long there is to go. You can always look me up, and there's a slide about me at the end. I prefer to get straight into the talk. It's just lovely to be here and physically be here. It's very nice to get back to some sort of normality. So, reliability engineering, what is it? One view of it is you're trying to minimize failures. But minimizing failures is kind of impossible. Well, minimizing isn't impossible, but eliminating them is. So from my point of view, it's about failure management, managing the failures that you have in your system, or that you can have in your system. And failure is inevitable. You can't stop that. No matter how careful you are, there will be things outside of your control that will cause failures to happen, including the famous one of a contractor outside the data center just cutting through the cable to the data center. That's actually happened. And reliability is actually a very expensive thing. So there's some low-hanging cheap fruit, but most of it's quite expensive. So it's about managing it, not really eliminating it. And I wrote an article over there on the cost of 100% reliability. And that's, so what happened was that Amazon is the only company that has a major product which is announced as 100% reliable. That's their DNS Route 53 product, which they have a guarantee. They actually guarantee it 100% reliable. And it's the only major product out there that has a guarantee of that. If you look at the fine print, it's not actually 100% reliable for everyone all the time. It's 100% reliable generally, but it can be out for individual customers or little groups of customers for seconds. I'm not sure how long. It doesn't really specify that. But it's still pretty impressive that they can even say 100% reliability on their entire product. And they gave a talk about how they achieve that. That's what that article is about, looking at that talk and finding out the cost that was involved in that. And it's very expensive. They have to do things like extreme levels of testing. So your average development has about an additional 30% of time or effort spent in testing. That's pretty average, 20 to 30%. Theirs is 90% of the overall time of development is testing. So that means that it's an order of magnitude larger in testing. And not just that, but they also have to hugely minimize the features that get into the product. So most of the time when they get somebody coming along and saying, can we put this feature in? The answer is no, because it'll make it slightly less stable, and we can't afford that because it's 100% reliable. Or they have to think about how they can put that feature outside of the main path so that it doesn't affect the reliability path. And there's a whole challenge. If you're interested, you can just Google me, and it's on Medium. I've got a series of articles on reliability on Medium, and it's actually quite interesting, the amount of different things they have to do to achieve that. But the upshot is that the more reliable you want something, the more expensive it's going to be. It's going to be quite expensive. And so it's not about eliminating reliability, it's about choosing the level of failure that you're willing to live with and how much that failure costs compared to how much you have to spend to achieve that level of reliability, of lack of failure. And obviously, if you have a failure, you get an incident. And so a lot of this work was when I was previously at Expedia, and we had a lovely monthly meeting about the incidents there and it was headlined as an unplanned investment. And if you think about, say, the most recent major outage is the Facebook one, the one where they were down for 6 hours or more, caused by them taking their own system out of the internet, basically. And that cost them, it's conservatively estimated as $100 million. So if Facebook is going to invest $100 million, they want some kind of return on it. And so if you think of your incidents as costing 100 million, that's equivalent to, if I didn't have that incident, I'd be able to invest 100 million. It's 100 million worth of investment. So that is an unplanned investment. Every incident you have is essentially an unplanned investment because it's going to cost your business something or other. And that amount of money could be invested somewhere else. So you have to make that decision. And sometimes, actually, maybe it's worth 100 million to be out for 6 hours to not fix this. Probably not in their case, but in some cases it is. The thing is, if you have incidents, it is an investment. It is money that your company is spending, even though it's unintentional. So make the best of it. Make sure that you use the information from that incident to improve your system. Make sure that you have these aspects. And so this, when I see incident categorized across most organizations, they tend to be, it's in the booking system, or it's in the landing page, or it's in, they're categorized according to the development teams that are responsible. And that's kind of useless in terms of figuring out how to improve your system, because that doesn't matter. So the way to categorize them best is to come up with a pattern that's useful for you to learn from. And this sequence here, this set, is not exhaustive, but it's actually the most common failure patterns that are out there if you look at incidents that are out there. So not the majority, but like a large percentage, I think over 15, maybe 20%, are just because you're not monitoring something. Over on the right is another article I wrote about the three biggest. I wrote this before the recent Facebook one. The three biggest outages over the last year. In fact, these are all bigger than the Facebook one because all of these are companies that are the web infrastructure. They provide infrastructure for lots of other companies on the internet. So when they go out, they take out a whole host of other companies with them. Whereas when Facebook goes out, it tends to take out just its brands and maybe a few of the companies that have their little apps on Facebook. But so if you add the Facebook one, those are the four biggest ones, and they're all caused actually from the bottom one of this list, a latent bug. Every single one of these, including the Facebook one, which, although it's a human error, which triggered. So what happened was that a guy took out the Facebook, basically the way Facebook was looked up on the internet, and that was removed from the internet, so you couldn't actually see Facebook. That's a human error. It was a human error, but all of our IT industry has to assume that human errors will exist. You can't blame a human error for a problem. There has to be systems in place to prevent a human error from cascading into some serious problem. And in Facebook's case, there was actually a check for exactly what was happening. There was a check within the script, but there was a bug in that check. There was a latent bug that hadn't been found, and so consequently, the human error propagated out and caused all the problem. And all of these other incidents were all caused by a latent bug. And and it's not really surprising that there's commonality, because the thing about a latent bug is that it's down there in the system, you don't know about it, and so it can arise at any time, and you don't realize. So a lot of SRE, that's site reliability engineers, your main focus is on what's recently changed. And so if something's changed, if you get a problem in the system, you look at what's recently changed. And the thing about latent bugs is they're not recently changed, so you're not quite sure about it. So, for example, the Google one was they rolled out an update to their major, it was their resource management system, and there was a bug in it, but it wasn't identified at all. And it didn't surface. And it didn't surface until, I think it was about 6 weeks to 2 months later, when a different update to a different system kicked in and basically triggered that. And the same with Amazon's. In Amazon's case, the latent bug was a design pattern that they were using, which was a single connection per thread, which everybody, not everybody, but architects should know is not necessarily a very scalable design pattern. But even so, it works as long as you don't run out of resources on the system. And what they did was they ran out of resources on the system. So it was a latent design error that they had there. And it was compounded in their case by the top one, monitoring inadequate. So they weren't monitoring that the file handles in the system were reaching what the system was capable of handling. And if they'd have been monitoring that, they would have not had what turned out to be a very major outage for, I think it was the US West region went out. So each of these is very interesting. But what I'm saying here is that when you have your incidents, review them, do those postmortems, and categorize them by a sort of pattern like this. I can recommend this as a good starting point. And this order tends to be, in terms of volume of incidents, what causes them. And monitoring inadequate is the biggest, but then the rollout procedure is the second biggest, and that's, you just haven't tested the rollout procedure. So insufficient testing is, it's more about, that you've got these features in your new version, but you haven't added tests for them. And that's really common to do. So you get these really well covered test coverage when you start out, but then it's sort of, you failed to keep up to date. And as you add features, you fail to add new tests, and that's very common, and that's quite insufficient testing. And then you also have this thing where you've got pipelines, and the pipelines take longer and longer, so you start splitting up the pipelines in parallel, and the testing one goes in parallel to the deployment one, and then you get test failures on the testing pipeline, but the deployment just carries on because it's a parallel pipeline and there's nothing telling it to stop. And that's quite often where failures get ignored. And then the something expired one is just, that's probably my favorite one, because we've had password expiry for, 30 years in IT, and it's still a problem. And certificate expiry for 20 years, and it's still a problem. So that's a fairly good way of categorizing incidents. If you are completely new to reliability engineering, or you're just trying to put reliability into your system, this slide is your biggest bang for the buck. This slide is where you start, because this will give you the largest amount of reliability into your system for the least cost. It's not free, though. And basically make sure that you have an ability to roll back. So I think I've got a poll online, which is, do you test your rollback capability? And here I'll ask you, do you test your rollback capability? Hand up if you say yes. Hand up if you say no. And hand up if you say, no, I don't know, we don't have a rollout capability at all. Okay, not bad. So most of you don't test your rollback capability. So think of it as an undo. And our industry has moved to the concept of undo. So we used to have, if you think about your word processor, it used to be autosave every 5 minutes, autosave at some custom thing, and then if it crashed, you lost 5 minutes and you had to go back to the previous version, or you lost everything if you were using a badly configured one, or one that wasn't autosaving because you didn't know about it. And we've moved completely to any document you do now, it saves everything you do, but it can undo it. And that's really, really great, because it means that you don't think about at all saving. You don't think to yourself, oh no, when was the last time I saved? When do I need to save this document? You don't have to worry about that. It's all saved, and you can undo. You can get back to where you were. Now, sometimes it's easier to not roll back. Sometimes it's easier to not undo. It's easier to change it. But generally, you're much happier writing your document knowing that you can undo anything you do, and it's all saved. And the same concept should happen for your deployments. And it also makes it much faster when you're working away. You don't have any cognitive dissonance about, oh no, is it saved? You don't have to worry about that when you're doing your document. And the same is exactly for deployments. If you have a rollback capability that you're comfortable will work, then you can be much more comfortable about rolling out. So this is the biggest thing you can do, is to make sure that you have a rollout and rollback capability and that they're all tested. There's a few other useful best practices when it comes to deployments. And the whole reliability engineering industry is about minimizing manual steps. That's one of the major things we talk about. You try and automate as much as possible. And that's because, as I said in that very first description of the Facebook one, is that you have to expect human error. It's absolutely guaranteed to happen. So if you minimize the human input, then you're minimizing human error. So manual rollouts you should be moving to a one-button click rollout as far as you can. If you don't have that, then a checklist that covers all your steps enormously reduces errors. Make sure that you've got all the artifacts well-defined. And so now when you've done the rollout, you want to be able to detect when there's a problem with it. That's really important. And the quicker you can detect it, the quicker you can roll back, the less the error impacts your system. And that's down there, the SLO's service level objectives. It's a buzzword been around for a couple of years now. And it's the targets. It's the goals that your systems should be achieving, throughput or the lack of error, the amount of errors, the percentage errors, whatever it is within your system that you monitor. You probably monitor it manually. You want to be able to monitor that automatically for a deployment so that you can see that if it changes, you want to roll back. And there's a number of different rollout patterns. And these aren't alternatives. You can do all of these. A canary is a small portion of traffic to a new version. So if you think about it, you'd have 80% of the traffic going to your existing version, and then two little clusters, one which is the new version and one which is the old version, and you send 10% of the traffic to each of those. And that's so that you can do a baseline comparison of your old version with the new version. And then that means that you can do a direct comparison rather than any kind of, otherwise you have to do the 80% compared to the 20%. You don't want to do that. So that's the canarying. Blue-green, this is where you have both of them fully available. Again, that's another of the costs for the Amazon DNS service. Because it's 100% reliable, they have to be able to switch to the old or the new at any time, which means that they have to have a full rollout of both versions completely available. And if you think about that, they're doing it across all the regions globally. They've got hundreds of availability zones. It's incredibly expensive for them. They actually came up with an entirely new way of sharding. It's called shuffle sharding in order to make their 100% availability. And it was where, if you think about a shard as, in this case, it's a cluster of customers. So if you have a cluster of customers over here in this shard, which is just, say, in one availability zone or one data center, if that goes down, you don't want to have all the customers impacted. So obviously you have a failover capability, and they're all here. But so that would be that's sharding partitioning. That's standard in a database where you'd have the replica and the original. What they came up with is an idea is that what happens if both of these go down? We lose the service for all of these customers. We don't want to do that. So let's make this a bit more reliable. Let's take this replica And instead of having a replica, let's slice up all of the customers in this one and put them in different replicas. And they do that for all the replicas. So if this one goes and this one goes, it doesn't affect a single bunch of customers, because all the customers here are actually now in lots of different. So there's a very small fragment of customers that get affected if the primary and the failover fail. And that's called shuffle sharding, and it's a technique they came up with in order to make their product more reliable. But that's a segue about the blue-green is just them having two complete deployments available. And then AB is standard, and it's become much more than AB now, ABC and so on. And that's where you have new features, but you'd have them turned off, and then you selectively turn them on in the new version. And again, you'd probably combine that with canarying, so send some of the traffic to the new feature. And then this is really become a big thing in machine learning, because there are a lot of in machine learning, you're trying out a lot of different things at the same time. So what they have is it's called a multi-armed octopus, and you have a lot of different features, and you send the request to all of them, and then it uses a kind of stochastic analysis to gradually eliminate the ones that are worst performing and sending more and more requests. But that's much more sophisticated. If you're starting out, just have your features deployed, turned off, and then turn them on. It's a very good way, because you can quickly turn them off again if there's a problem. So I'm going to shift over to a different thing here, which is about Kubernetes and reliability engineering. So Kubernetes has taken our industry by storm, it feels like. Even a few years ago, it was you were risking if you chose Kubernetes, and now it's standard, everyone uses it. And if you know the history, Kubernetes came from actually the reliability engineering projects within Google. So it's not surprising that actually the reason that Kubernetes has taken our industry by storm, the reason it's dominating so much, is because it's built to make your system more reliable. Which means that if you use Kubernetes, you are actually having reliability built into the infrastructure of your system. I've got a second poll here, which is, I'll say the same wording as the online one. Have you or a colleague created a keep alive script or utility or daemon or component? Hands up if you or a colleague has done that. So a keep alive script is one where if the service goes down, then it starts it up again. And that's okay, so not many people here. I don't know about the online one. In my experience, I've seen a large number of keep alive scripts. And if you do a search online for keep alive, you'll find like so many different implementations. You don't have to implement that because if you've got Kubernetes, because it gives you it for free, as it does a lot of different reliability features. I mean, I haven't intended this to be particularly readable. I just wanted to start listing them. There's actually a lot more than this. I just went through and I think that was about I got to 15 or so, and then I stopped listing them. But there's all sorts of things like that keep alive. Like if there is a problem with a node, then it will just move everything over to a different node. And that used to be a real serious problem in operations, where if a node went down, they had to get together and try and figure out where they were going to move things to. All of that comes for free. So Kubernetes, the reason Kubernetes has taken our industry so strongly is because it is reliability in your infrastructure. And if you're not using Kubernetes or something similar, well, it will be Kubernetes, then you're having to implement a lot of that reliability into your infrastructure, which is a lot of effort. Now, it doesn't come for free, okay? Kubernetes is not simple. You have to get used to it. It's got a lot of effort around it. But then it's quite good for reliability, so you have to pay some aspects for reliability. And then a second thing that's taken our industry by storm is NoSQL data stores. And again, the reason is also reliability. So yeah, it might be counterintuitive because you think, well, hang on, they're not consistent like a relational database, so why is that more reliable? So there is a fundamental computer science theorem called the CAP theorem, CAP theorem. And the C and A and P are those things over there on the right. C for consistency, A for availability, and P for partition tolerance, which means that the last one means that if you have a network problem, you still get a valid result for a distributed data store. And the thing that the CAP theorem says is that you can only actually have two of these. You can't have all three at the same time. And if you look at so that means the intersection is the bits that are interesting, the CA, the CP, and the AP. And if you look at those intersections, the one over there, top right, CP, that's caches, okay? That means you have consistency because you get it into a cache, but if the network goes down, then you might lose your cache. And you shouldn't care, because that's the whole point of a cache, is that it's not the primary data. So if you lose the cache, you can always go to the primary data store and get it. So that's fine for caches, but it's not fine for a data store. And over there on the top left, that's where relational databases lie. That gives you the full consistency and availability on a particular node, but not distributed availability at the same time. So that's ideal if you need consistency. And there's a few things that absolutely do need consistency, strong consistency. Payment things specifically, and things like payments. That's very important that you have consistency there. Nobody wants their customers to find that they've made some kind of transaction and it doesn't show both sides of that transaction. But for most data in our modern industry, you don't need that. It doesn't matter if you're a few seconds out of date on your tweet. If somebody updates their Twitter feed and you don't see that immediately, you don't care. If somebody updates their social network and you don't see it immediately and it takes a few seconds, even minutes, you don't really care. You don't even notice, to be honest. So that's why down there in the AP area, the availability and partition tolerance is kind of where our industry has moved a lot of our data to. And that's eventually consistent data. So it means that if you go to the data store to get a data item, then you might find you're getting an old one rather than the latest one. And that can happen for a few seconds typically. And that's fine. That's fine for most of it. But you just have to be aware that that's the case. And that's more reliable because you've got AP, the partition tolerance. So it means that if you've got network problems, which happen all the time, you still got service, you're still getting data. And that's why the NoSQL data stores are taking over, because of the reliability, the additional reliability you get. Within your system, as I said, reliability is about failure management. So if you're going to say, a certain level of failure is acceptable to me for these services, you have to decide. So obviously some services are more critical than others, and you have to do that separation of services. You have to decide which services need to be up for longer, which services need to be can be out for longer. And this has become fairly standard to divide your services into tiering, where the top tiers are the critical services, and then there are gradually graded down. And you need to do that so that you need to know how much effort to put into making those services more reliable, or not to put effort in to make the services reliable. So an important service which will not impact operations for a while, it can be out for a bit. If you're used to Kubernetes, that would be equivalent to having one pod and it goes down and Kubernetes will restart it within a certain time period. And that's the sort of thing, that'd be fine. Whereas if you wanted a critical service, then you'd have to have pod anti-affinity with them in different data store, different availability zones or data centers, multiple pods, so that if one goes down, the others still stay up and carry on servicing. That's the sort of thing that you have to think about, and you want to categorize your services in those tiers. So I've got one last poll, which is, does your CI pipeline include any of the following tests? And I've got performance, security, load or stress, and none of these. So or any of those. So put your hand up if you've got one of these in your pipeline, in your CI pipeline. Keep your hand up if you've got 2 of them. Keep your hand up if you've got 3 of them. Okay. So, I mean, it's not surprising. They're difficult to do, and they take time, and they're on that parallel track, so that the deployment and even the functional tests are always finished before these get finished, for the most part. Maybe not the security tests, which can be quite quick. But a lot of people just, I can't do that, and it's a different track, or it's a different time, or just once a month we'll do performance testing, or once a week on a completely different pipeline. But the reality is that all of that is making your system less reliable. So the more of these testing that you can put into your CI, even if it's on an occasional basis, the more reliable your system will be. And chaos testing, you can put in your CI pipeline, but it's intended to be in production. So chaos testing, if you've not heard of it or not come across it, it's not actually randomly killing stuff off, which is what it sounds like, just be chaotic and do stuff. Chaos testing is you come up with a hypothesis, like if this network here is a bit slow, then the latency of this request will go over our SLO. And chaos testing will test that particular hypothesis by putting some sort of degradation, artificial degradation into that pipeline, into that request pipeline there. And you can do that in production because you do it on a small section of your traffic. And similarly, you can kill off nodes in production because if hopefully you've got a reliable system which can handle node failures or pod failures. And it's the sort of thing that is really taking off within the industry, but it's not just completely random failures, okay? It is very targeted hypothesis. If this thing is problematic, then this is the result we expect. You test for that. Or, more to the point, we have this reliability feature in there. We know that if the node goes down, service will be uninterrupted because Kubernetes will restart the services over there. And you can't just rely on the fact that Kubernetes can do that. You should be testing this. So I've done this kind of testing, and if you get the configuration wrong, then it doesn't work because you can have your system set up to be in multiple availability zones, data centers, and you can set it up so that you think that they're distributed, but they're not. And if one availability zone or data center goes down, then you actually lose the service when you're expecting it not to do it. Because Kubernetes, for example, doesn't really handle multiple availability zones and data centers very nicely unless you make a lot of effort to do that. So these are the things that if you have a reliability feature, you should be testing it with a hypothesis and do it in production because after all, it's a reliable feature. Obviously, do it in test first, but if it passes the test, do it in production. Okay. This is, that picture over there on the right is the Falcon 9. It's got 9 engines, that's why it's called Falcon 9. And it's, if you've seen the recent SpaceX Dragon that went up with the 4 astronauts who were trained, but they were civilian astronauts. They weren't military or anything. None of them was a trained military astronaut. I think it was the first time ever that that's happened. So normally all of the flights have had like one pilot who's been trained, and this was the first time it happened that they had deliberately no astronauts who were like trained as pilots, and it was all successful. So you might have seen that. It was a big news item. This was back in 2012, and it was the first commercial launch of the SpaceX Dragon. It was actually carrying cargo to refuel the space station, and it is a lovely example of reliability. It has 9 engines, and it only needs 7 to succeed for its normal flight. On that first commercial flight, one of the engines failed. And the other it didn't affect any of the other engines. So the other engines are all fault tolerant. They were tolerant to the faults to one engine, as was the whole rocket, as was the flight path. And then in real time, the onboard computer recalculated the flight because obviously with one engine out, it's going to sort of shift the aim that it's going at. It needs to recalculate how much energy how much force to push out of the other engines so that it carries on the normal flight, and it did that. So it's an excellent example. It's got redundancy because it has 2 extra engines. It was fault tolerant because there was a fault, but it didn't affect any of the other engine. It didn't affect the rocket. So it was tolerant to the fault. And it was highly available because it just recalculated and carried on. And it was a very successful refueling and came back all very nicely. And it's a perfect example of a reliable service. So these are the concepts that you need for reliability for developers and for architects. The basic ones are these 3: availability, resilience, and adequate performance. So availability is kind of obvious. Is the system there? Is it up? Can I actually send something and get a response? Resiliency, as you saw from the rocket system, that's the ability to handle a failure of some kind and still carry on. You might not get the same quality of response, but you'll still get a valid response, something that's good enough. And this last one, adequate performance, people don't necessarily think about, but you can have an available system, it's up, and it's sending a response, but if it's sending a response so slowly, you're expecting it in a few hundred milliseconds and it takes minutes, it's not good enough, right? And this is something that you see all the time on browsing, is if the browser, you go to a page and the browser doesn't come back, doesn't show anything for like even a couple of seconds, and you think, oh, sod this, I'll give it up and go to do something different. So that means it's not reliable if it's not performing adequately. So these are all the basic items of reliability that you need to measure. And there's a bunch of high-level concepts for resilience. And data replication that's just that distributed storage that you want with copies, replicated copies. And process replication is multiple instances, and that's a very standard thing, clusters of instances. Containment and isolation is about minimizing, if there's a problem, if there's a failure, you want to minimize what that affects. So you want to make sure that the failure doesn't cross boundaries and go over to affect other systems. High availability we talked about just now. And then these are the last of these resilience high-level concepts. Fallback, and so there's one thing, there's only one letter difference between fallback and failback, but they're very different. So fallback is you make a request and it's a degraded response because it gives you a less useful response. It's falling back to a different mechanism to give you a response. And failback is after failover. So if a system fails, you fail over to the backup, and then when you fail back to the main system because it's back running again, that's failback. And fail fast is quite important in your system, so that the quicker, if something's going to fail, you want it to fail as fast as possible, so you have your failover or fallback responses available to trigger quickly. So that's all part of gracefully degrading your overall system. And then there's some basic resilience patterns and practices. So you get a lot of these coming with circuit breakers. And I don't know if one of the earlier talks was talking about a mesh, the service mesh that's now becoming part of Kubernetes. I don't know, Istio or what's the other one? I forget, but Istio is one of the service meshes. And it's the idea of having these extra little services that are sidecars to your application services, and everything routes through them, and they can cut off if there's a failure. They can terminate and then recover when the upstream service recovers. They can also limit the amount of traffic that's going to your service. They can reroute traffic. So all of that's what a service mesh is providing. So if you're not using a service mesh, then you should be putting that into your application. And there's a lot of frameworks to do that. I think for Java, which is what I'm most familiar with, the one would be resilience for J. It used to be Hystrix, but then that was Netflix's one, and they've actually moved over to a service mesh, so they've deprecated it. So I think it's resilience for J for Java. But the move is to move over to a service mesh again. So that's becoming part of our industry. It's a bit early days still, but it's becoming part of our industry because of the reliability that it gives. It's a bit early days because the problem with these things is that when they go wrong, you need to be able to fix them. So there's a lot of information and a lot of experience now about if something goes wrong in Kubernetes, you can figure out roughly, looking up. But that information is not still there in service meshes. So if things go wrong with service meshes, it's a big effort to try and figure out what the problem is and where things are going. So it's not really mature yet, but you should either have service mesh or a circuit breaker in your system. And then for availability and performance, a couple of slides. I wrote this article. So this one is about overloading your system, and this is quite good because there's actually only 6 things. It's very, very contained in order to avoid overloading. So you can either those top 3 there, you can either scale over provision or queue. So scale your system up to handle extra load, or over provision, so have the extra capacity to handle the extra load, or queue up requests if you have a system which is capable of queuing. And when you get to the limit where you can't do any of those, because at some point, because you haven't got an infinite amount of money, at some point you can't do those, then there's a matter of the bottom 3, which is you have to start dropping traffic, or you have to throttle the traffic, which is, so dropping is, you drop it completely. It's like when you go to a web page and you never get a response. That's that one. Throttling is, you'll get the error message. You'll get a page not available. That's the throttling. And then the last one, back pressure, is actually throttling where your client understands the error message and doesn't send as many requests per second or per minute as it was before. So that's just a combination of throttling and the client holding back on requests. And then the other aspects of availability and performance patterns, make sure you have those service level objectives. Do have dashboards and alarms. So these are all sort of basic things that you should have, and health checking, of course. It's actually, they're fairly basic. There's not a huge amount there to try and implement in a system. And observability, understanding exactly what your system is doing, well, not exactly, but even approximately what your system is doing. APM, application performance monitoring, is the tool for observability. And I work for Elastic, as you can see down there at the bottom, and we have Elastic APM, which is a very, very nice tool for observability. But that's the basis there of understanding. And remember, if you go way back to one of the earlier slides where I said you categorize the failure patterns, monitoring was the most common reason for failures. Well, it's lack of monitoring. It's the most common reason for failures. And the whole point of an APM tool is it will observe your system and show you, it will monitor a lot of that, fill in that monitoring gap. So you should, because you can get free versions of everything now. You should be able to put an APM tool into your system. And then, nearing the end here, just this slide and the next one, some final reliability concerns that are very important. So the thing about usability is, it doesn't sound like it's a reliability concern, but it is, because if you find something difficult to use, so does lots of people, and then they all do the wrong thing. And that means that you're increasing the chance of human error. So the more something is usable, the less chance there is of human error. And human error is what is the starting point for a lot of failures. So that's something it's actually dramatically important. But I I can't do lots and lots of slides on usability, but it is actually very, very important, and it's very difficult to get right. It's a lot of effort and a lot of interaction with people to get the usability right. And then quite often when there's an incident, everybody jumps to the conclusion that it's the network, because often there's a problem that looks like it's a network problem, but it usually isn't the network. However, sometimes it can be, and these are the kinds of things which are very typical if it is the network. These are the things to start with when you look at, and making them more reliable is really actually very, very expensive. So it's often the level of reliability that you have with modern networks is usually good enough for most applications. And then the final point here is that written assistance. So you should have all of these things, and kept up to date, which is the really difficult thing. And so the idea is that you not just say what the service does, but somebody coming fresh to it when there's a problem wants a very quick overview of what the service does. So you want that to be very simple and straightforward to understand. And then you want to tell them these are the steps you need to get to figure out what problems there are, and then it's the process of escalation of if there is a problem and I can't figure out, or I figured out this, who do I contact next, and who should they contact if I can't contact them, or who else should I contact? All of that is really important for making sure that you can mitigate a problem that exists. So, as I said, there is a slide about me, but you can always look me up online. So I'm going to go back to what I told you, this is the last slide, which is the biggest bang for your buck if you're just coming to reliability. Make sure you have a rollout procedure and a rollback procedure that work and are tested. And that's it. And I'm happy to take questions now. Yep.
Thank you. Thank you so much for the talk, by the way. I really enjoyed it. You've done a poll on different types of testing and security, fault injection, and you mentioned the more types of tests you have in your CI, the more resilient your system is. And you've also mentioned that even if you do it not on every commit, but still maybe once a week, once a month, I appreciate there's no one answer for this, but maybe how you've done it at Elastic, how you figured out that frequency, or how long your CI can be, if it's 20 minutes, or is it an hour, is that acceptable? How you figured that out?
Okay, so the question is, all the tests that you can add, the additional testing that you can add to your pipeline, how have we figured it out? What's best? And the answer is we haven't figured it out. Just like every organization, you're trying more, you're trying to make it more reliable. In the case of the parts of the Elastic that I work on, which is the agent, it's not quite, we're not producing a system that's going out to live. That is, we do that in other parts of Elastic, but in the part that I'm working on at the moment, we don't have that, so we don't need, for example, chaos testing. That wouldn't be relevant. Performance testing is relevant, so we do try and add benchmarks in there, and we do that occasionally. For systems, so previously I was at Expedia, and that all of those were relevant because all of the systems went to live websites, and there the emphasis was to put as much as was reasonable. So it was reasonable to put performance testing into the pipeline, but not for every commit. It would be a separate branch happening once in a while. And also load and stress testing, because once you've got performance testing in there, it's worth putting those additional ones because they're just higher loads. But a lot of the emphasis was instead on chaos testing, and it's true for our industry. A lot of emphasis is now moving to chaos test for reliability, and moving that to just do an initial test in the non-production environment so that you validate your hypothesis there and that it all works. Because if you find a problem there, then you don't want to do it in production. But if it's working in the test environment, then start moving it into production environment, and do your hypothesis testing there on a regular, automated basis. Because you should have the situation where your system can handle those without any degradation of the system. That's your hypothesis usually. I've put this reliability capability in there. If we do this, there should be no degradation. So let's test it. And if you carry on testing that in production, then you're as reliable as you can be. That's the best answer I can give you. Okay, thank you very much. Okay.